Now that we have our base frames, what if we want to control some of the dimensional qualities of these frames? Say maybe the thickness, but we want the change in the thickness to respond to the frame's proximity to a point. So this is what we know as an attractor point, where a point controls what these objects start to do. Some of you would like to use Rhino points. To keep things more parametric, I'm going to use a Grasshopper point, and I also want my point to stay within the boundaries of my facade. So let's get into it. I will start by just turning off these surfaces and turning on my facade boundary surface. Now, to get that point on the surface, we're going to evaluate the surface. Connect that here, and it requires a point relative to the surface. What we can use is something called a multi-dimensional slider, which is MD slider. How this works is, so when you think about a slider is one direction, goes from point A to point B. But remember, we're dealing with a two-dimensional object, and so we're trying to get a value along two dimensions, and so that's where this comes in handy. Just going to plug this in here, delete that, and you'll notice, I'm going to zoom in, as I move this around, it moves. But when I move it to its maximum point, you notice that I'm not able to get to other parts of the surface. The way I do that is to reparametrize this surface. Probably wondering what that means. So when you reparametrize a surface, think of a surface as having a length. Okay, so it's from 0 to x, and a height, in our case 0 to y. What reparametrize does is it converts the domain. Remember, we realize that a surface is a domain that operates in the u and the v. So that is the u and that's the v. What it does is it changes the value of the length from whatever it is, x, to 1, and the height value to 1. That's what reparametrize does. And so because our MD slider goes from 0 to 1, you notice that's the max, we're able to then use that so that it can reach every facet of the surface. Okay, that's how we get that. I'm gonna delete this, and now what we want to do is establish a relationship between this moving point and our frames. So how do we do that? Well, remember, we can get the area centroid of the surfaces that we created, okay, and then get a distance between them. So distance between the centroid and this point. Well, now let's make this visible. Instead of getting the distance, let's just draw a line from here to here. See, now notice as we move this moving point is maintaining a relationship with all the points. The line is just to visualize it, but it's the same thing that's happening here. In fact, I'm going to put a panel here, and you will notice that as I change, the values change, and that's because this is the distance relationship between all these points and the moving point. What we want to do is use these values to control the distance of the offset, which is what's controlling our thickness of the frame. To do that, what we want to do is remap this number. Okay, so we do a remap, and essentially what a remap does is it takes a list of numbers, which is value to remap, and takes a source domain. So a source domain defines the maximum and minimum values in this list. So let's sort this list so that we can see the maximum and minimum value. Okay, so we have that. The maximum value is 47.6 and the minimum value is 3.1. But how do we create a domain? Because that's what it needs, source domain. How do we get the domain relative to this list? What we can do is something called bounds. Okay, that takes, let's put this here, that takes a list of numbers and gives you a domain. So notice that the first value is that and the max value is that. So right now we have the max and min of the values, numbers in this list, but we want to convert these values to something that fits within the boundaries that we're willing to tolerate for the distance. So what we want is we want the closest frame to this point to have a distance of 4, and then the farthest to have a distance of 15. What we're going to do is create a target domain. So if you notice, this is asking for a target domain, so it will convert the numbers which are in this domain to new numbers which are in this domain. Okay, so let's construct a domain, and I want 0 to 15. I'm going to connect that here. I'm going to connect that here. So that means, let's see what's coming out from here. Notice now we can control this domain, but we want 4 to 15 for now. We can always change it. That's the beauty of using sliders. So I'm going to feed my list of values, and there's domain and the target domain. And let's see what we get coming out. Well, we get a list of new numbers. Okay, you're wondering, so what just happened? Well, think of a domain. This domain is 3.18 to 47.6, and we have our domain from 4 to 15. Okay, now this number, let's get out of here. The first number here is 36, and so that means 36 will fall somewhere here. I'm assuming 36. So this point here is somewhere here. It means that this value is going to be somewhere close to 12. So that's why we have this value here, because relative to the position of 36 in this domain, what is the value in that same position in this domain. That's exactly what Remap is doing. It's giving us positional information relative to domains. Okay, so 36 in this domain is equal to 12 in this domain. And so if our domain was 0 to 1, our value here will be 0 point something, maybe 0.8, maybe. But that's how we get these values. So now we have a value. In fact, if we check the domain of this value, or the values coming out from here, okay, notice that it's from 4 to 15. That means we can pass this value into the distance. Let's get rid of this, get rid of this, maybe move this way, just tighten this up, delete. As we move this point, see what, if I hide surface, there we go. See that it's changing, but we want it to maybe have some more visible change. So I'm going to make the max. Now you can see as we move, there's real visible change. Now this is how you create an attractor. There's a relationship between the points, and because it's maintained the list address such that the address here is the same as the address here, we're able to change information and pass it into where it needs to be. So we'll clean this up. Okay. And hide our centroid. Okay. You can even hide this point, but you just won't know where your pointer is. So keep it on. But you notice that the Falloff, like we'd like to have control over this Falloff that's happening here. What we want to do is disconnect this target, move this down, create a new remap. Right now these values coming out are going from 0 to 1. In fact, we can confirm that we're doing the bounds, connecting that here, see 0, and that's because the target value or target domain is going from 0 to 1. We want to keep it that way, and we want to pass that value or those values into here. And then this source, instead of going from 0 to 1, we want it to be dynamic. That will be our Falloff. So we construct, or Falloff control. So we construct domain, and then we want our value to go from -1.0 all the way to 1. Okay, and do the same thing. We can control that. We put that in here as a control for Falloff, and put this in here as a control of what our panel sizes will be. Now what we want is to use the clipped. Okay, now I'll show you the difference between the values coming out of clipped and the values coming out of mapped. And also this values. This is 1. Okay, so any value right now, the values coming out of here are from 0 to 1, but we have a domain that is from -1 to all the way to 1. Okay, so any value, and you notice we have the maximum domain here at 0.5. So any value from here that is more than 0.5, it converts it to 0.5, such that if 0.5 is the max here, the maximum value here is what it will return. So if I make it, so see that we have 0.75 here, I'm going to make this 0.8. You will see that these 3 values stay 24 here, but this third one will change. Okay, let's try that. Make that 0.8 or 0.7. There we go, 0.8. So see how, because this value is below 0.8, this value remains 24. So if I make this, let's see what's here. Yeah, so it's clipping these values relative to these values and assigning it the maximum relative to this. So any value coming out of here that is more than 0.8 will be remapped to be the highest. Okay, so if we connect our clipped value to here, okay, now you notice that we can control the fall off, okay, spread, and also the dimension. So now we have fall off max, let's call it that, or min. Fall off max. Thickness min. Thickness max. So take that away, and now we have better control and reduce this if we want. That goes away. Reduce this, increase it if we want. Give us some more variation. So we can start to play with the spread, not just the dimension of the thickness. And that's how we create an attractor and use a point to control some of the qualities of this frame. The next thing is, what if we want to control it with multiple points? For this, I'm going to use a Rhino point. So to activate my point in Grasshopper, I'm going to instantiate with curve, point. Set 1 point. And we're going to do the exact same thing we did with this point. Is create a distance relationship between all of these points and this point. So the same thing that's connected and we do the same thing. Let's move this way. So now we have these two distances. In fact, let's visualize this with the line. Okay, so we use that and we use that, and you notice as we move that, same relationship. Okay, but how do we establish, right now these two things are working independently, how do we get them to work together? We have values coming out of here, values coming out of here. Well, to get these 2 points to work together, we will do a mathematical operation on them. So we'll use multiplication, so that as this changes, this value changes. As this changes, this value changes. And what that is, the value coming out of here, this value is a multiplication of the value in the first index in that list and the first index in this list. That's how we get this value. And so the second value and the second value, that's how we get this value. So it's a list, it's multiplying the values relative to their corresponding indices, relative to their corresponding index. Let's delete that, delete that, delete that. In fact, we can visualize this round. So we have to the nearest. Okay, so let's tag and use these points, centroid as a location and the nearest. Hide this. So now we can see as we move this, this changes, and also as we move this, it changes. So these 2 points are affecting these 2 points are working together relative to the frame distance. So now that we have this, all we have to do is feed this value into the values, because this is the value we're going to remap now, and feed this value so we are getting the right boundaries. Okay, so now that means as I move this point, see it's changing. As I move this point, it's changing as well. So if we wanted to connect a third point, all we have to do is copy this, put our point somewhere here, instantiate it, and then add it as an input variable to the multiplication. So now if we have a point that's here, we have a point that's here, you can see the 3 of them are controlling what this thing is doing at the same time. That's how you don't need this, just want to use 2 points, but that's how you set up attractor points, not just an attractor point. So you can do it for a number of points. The next thing we're going to do is see how we can use an attractor curve to control the dimensional quality of these frames.